Hello students, welcome to this video lecture on testing of hypothesis for large samples, part of the course Probability and Statistics. My name is Dr. Krishna Kumari and I'm an assistant professor in the Department of Mathematics at SRM Institute of Science and Technology, Katangulattur. This session is going to be the continuous session, part 2 of testing of hypothesis. Here we will be solving several problems involving large sample tests covering means. So let us begin. So in part 1 presentation, I have explained the fundamentals that are essential for understanding the testing of hypothesis, and I have also explained the procedure for testing of hypothesis in part 1 video lecture itself. Here I just want to repeat it so that it will be easy for you to understand the upcoming sums to be solved. So I'm explaining again the procedure for testing of hypothesis. So this is going to be the step-by-step procedure for testing a hypothesis. This 5-step process is what we follow for every single problem in this lecture. So step 1 is going to be setting up the null hypothesis H0, and step 2 is the alternative hypothesis H1, which decide whether it is a one-tailed or a two-tailed test. Step 3 is going to be choosing the level of significance alpha, typically 5% or 1%. If not specified, we default to 5%, which is 0.05. Step 4 is going to be computing the test statistic Z using the formula Z equals to T minus E of T divided by the standard error of T, all under the assumption that H0 is true. And step 5 is going to be comparing the calculated value of mod of Z with the critical value Z alpha. So if mod of Z is less than Z alpha, we accept H0, and if mod of Z is greater than Z alpha, we reject H0. So these 5 steps helps us to understand the testing of hypothesis procedure, and we apply them to every problem from here on. This is also again a recall of the critical value table. So before we solve problems, let us clearly define what constitutes a small sample and a large sample. A small sample is one where the size n is less than 30, and a large sample is one where n is greater than 30. So for a large sample test, the test statistic follows a standard normal distribution, and we use what is called the Z test. So now the critical values, the values of Z alpha used for comparison are named as critical values, and they are as follows. So for a two-tailed test at 5% significance, Z alpha is going to be plus or minus 1.96, and at 1% significance, Z alpha is going to be plus or minus 2.58. For a right tail test, that is one tail on the right, at 5%, Z alpha is going to be 1.645, and at 1%, Z alpha is going to be 2.33. And for a left tail test, that is one tail on the left, at 5%, Z alpha is going to be equal to 1.645, and at 1%, Z alpha is going to be minus 2.33. So this table is essential for drawing conclusions in every problem. Therefore, these values should be memorized. We now come to the third type of large sample test, testing for a single mean. So the first, we will be defining null hypothesis H0, which is mu equal to mu naught. So for some specified value, the test statistic is going to be Z equal to x bar minus mu divided by sigma by root of n, where x bar is the sample mean, mu is the population mean, sigma is the population standard deviation, and n is going to be the sample size. If sigma is not known, we use the sample standard deviation smallest instead. Therefore, the formula can be rewritten as Z equal to x bar minus mu into root of n divided by s. Additionally, we can construct confidence level for the population mu, that is at 95% x bar plus or minus 1.96 into sigma by root n, and at 99% x bar plus or minus 2.58 into sigma by root n. So these confidence intervals gives us a range within which the true population mean is expected to lie. Now we move on to the problems. So our first problem is that the mean lifetime of a sample of 100 light bulbs produced by a company is 1580 hours with a standard deviation of 90 hours. Test the hypothesis that the population mean mu is equal to 1600 hours against the alternative that mu is not equal to 1600 hours at alpha equal to 0.05. So for this, they have given the value n is going to be 100, which is greater than 30. Therefore, this is a large sample. And the sample mean x bar is 1580 and population mean mu is 1600. Sample standard deviation S is going to be 90. So according to the procedure of testing of hypothesis, our first step is defining null hypothesis H naught, which is mu equal to 1600, and the second step is defining the alternative hypothesis H1, that is mu not equal to 1600. So this is a two-tailed test because they have just asked us to find the difference and they haven't mentioned anything as less than or greater than. Therefore, the level of significance at 5% alpha is going to be, for a two-tailed test, Z alpha is going to be 1.96. So our fourth step is going to be finding the value of Z, that is the test statistic. So Z equal to x bar minus mu by S divided by root of n. So by applying all the values, we get mod of Z equal to 2.22. So our final step is concluding from the calculated value. So here the calculated value mod of Z is greater than the table value Z alpha. Therefore, we reject H naught. So the data suggests that the true mean lifetime of the bulbs is significantly different from 1600 hours. The company's claim does not hold at 5% level of significance. The next we are going to type 4 test, that is difference between two means. The fourth and the final type of large sample test here we cover is testing for the difference between the two population means. So the null hypothesis here is defined as H naught is going to be equal to mu1 equal to mu2. That is no significant difference between the two population means. And the test statistics is defined as Z equal to x bar 1 minus x bar 2 divided by square root of sigma 1 square by n1 plus sigma 2 square by n2. So the special case is that if sigma 1 is equal to sigma 2, then we just make it as sigma, equally known as standard deviation, and therefore we can rewrite the formula as Z equal to x1 bar minus x2 bar divided by sigma into root of 1 by n1 plus 1 by n2. If sigma 1 and sigma 2 are not known, we use the sample standard deviations S1 and S2 in place of sigma 1 and sigma 2. And next, obviously, the conclusion is going to be accepting H naught if mod of Z is less than Z alpha, and we reject H naught if mod of Z is greater than Z alpha. So now we can move on to the problems. The first problem is that uh, the mean yield of rice from a sample of 100 fields is 200 kg per acre, and from another sample of 150 fields is 220 kg per acre. So assuming the population standard deviation is 11 kg, test if there is any significance difference between the means of the two samples. So here for this, the solution is going to be n1 equal to 100 and n2 equal to 150, and here both are large samples because they are greater than 30. And x1 bar is going to be 200 and x2 bar is going to be 220. Sigma is equal to 11 and it is given same for the both. Therefore, our first step is going to be H naught, defining H naught, that is the null hypothesis. X1 bar is equal to H2 bar, that is there is no difference between the means. And the next step is defining the alternative hypothesis H1, that is x1 bar not equal to x2 bar. So this is a two-tailed test. And third step is writing the level of significance alpha is equal to 5%. So for a two-tailed test, Z alpha is going to be 1.96. So by applying the values in the test statistic, we get the value of Z to be minus 14.08. Therefore, the mod of Z is going to be 14.08. So from this, we can conclude that at 5%, uh, calculated value is greater than the table value. Therefore, we reject H naught. So there is a highly significant difference between the mean yields of two samples. The difference in rice production between the two groups of the fields is statistically significant. So this is going to be the conclusion of this problem. Next, we move on to the next problem. The mean height of 50 male students who showed Above average participation in college athletics was 68.2 inches with a standard deviation of 2.5 inches. Another group of 50 male students who showed no interest had a mean height of 67.5 inches with a standard deviation of 2.8 inches. Test the hypothesis that the students who participate in athletics are taller. So here they have mentioned the word as taller, just not as not equal to. Therefore, this is going to be a one-tailed test. So here N1 is going to be equal to 50 and N2 is also 50. So both are large samples. And X1 bar is equal to 68.2 and X2 bar is equal to 67.5. S1 is 2.5 and S2 is 2.8. Therefore, our step 1 is going to be defining the null hypothesis x1 bar is equal to x2 bar. And step 2 is going to be defining the alternative hypothesis h1, which is x1 bar greater than x2 bar. That is, we claim the athletics are taller. Therefore, this is a right-tailed one-tailed test. And step 3 is defining the level of significance alpha is equal to 5%. So at 5% level for one tail, Z alpha is going to be 1.645. Therefore, by applying the values, we get the Z value as 1.3187. So here mod of Z is less than the table value because here the table value is going to be 1.645. Therefore, we accept the H naught. So since we accept the H naught from the given problem, we can conclude that there is no significant, that is, there is no sufficient statistical evidence to conclude that the students participating in athletics are significantly taller than the non-participants. So this is going to be the conclusion for this problem. So this is going to be the entire summary for both the part 1 video and also this current part 2 video. So this is here I have just giving the summary for all 4 large sample tests covered in both the sessions. So in the previous session, first we saw type 1, that is for single proportion. So Z equal to small p minus capital P divided by root of PQ divided by N. So we use this when comparing one sample proportion to a known population proportion. And then we saw type 2, that is difference between two proportions. And the formula for that is going to be Z equal to small p1 minus p2 divided by root of pq into 1 by n1 plus 1 by n2. We use this type when comparing proportions from two independent samples. Then in this current presentation, we just saw type 3, that is for single mean, Z equal to x bar minus mu divided by sigma by root of n. So we use this when comparing a sample mean to a known or hypothesized population mean. Then we saw type 4, that is difference between two means. So Z equal to x1 bar minus x2 bar, which is divided by root of sigma 1 square by n1 plus sigma 2 square by n2. So we use this when comparing means from two independent samples. And the universal decision rule is simple. If mod of Z is less than Z alpha, that is if calculated value is less than the table value, we accept the null hypothesis. And if the calculated value is greater than the table value, we reject the null hypothesis. So this brings us to the end of this lecture. I hope this session has given you a thorough understanding of large sample hypothesis testing. So in the previous session, we covered the first two types, that is testing for hypothesis for a single proportion as well as for the difference between the proportions. And in this presentation, we covered the remaining two types, that is testing for hypothesis for a single mean and then testing for the hypothesis for difference between two means. So practice these problem types well. So these 4 types comprises the entire testing of hypothesis. Thank you students. Thank you for watching and best of luck.